These are the lesson 9.3 notes for day 3 on rational functions. We're going to continue graphing rational functions today. We're going to find holes on rational functions today, along with continuing to find vertical and horizontal asymptotes and x and y intercepts. So we're going to get right to this equation. I've already typed in this equation in my calculator. Remember that we've put this additional set of parentheses around the denominator because there are multiple factors down here. And when we graph this function on our calculator using our standard viewing window, zoom 6, you'll see that our graph appears to be an asymptote. Now remember, on newer calculators you won't see this, but you will see this curve on the left side and you'll see this curve here on the right side. It's pretty clear that 5 appears to be an asymptote here, and that's no surprise. In the denominator we would get a 0 if we plugged in 5 for x. So vertical asymptotes again are found by finding which values would cause our denominator to equal 0. Now it appears that you should use -2 as well. Our problem is that usually when we plug in -2 in the denominator and get 0, it's a vertical asymptote. But in our numerator, usually if we plug in -2 and get 0, that would represent an x-intercept. So what do we have? Do we have an x-intercept? Do we have a vertical asymptote? Well, actually we have neither. If you have a factor on the top and bottom that's the same, the 0 that corresponds with that factor is called a hole. More on this in just a moment. There are no other values that would provide us with unique vertical asymptotes or unique x-intercepts. This graph actually has no x-intercepts because -2 is actually going to be a hole. You may recall that for y-intercepts, we plug in 0 for x, and if you plug in 0 for x here, you're going to get 2 in the numerator. In the denominator, you're going to get a 2 times a -5, and this is equal to 2 over -10, which reduces to -1/5. You can call it -1/5. You could say y equals -1/5, 0 comma -1/5. You can use -0.2 if you want to. Any of those things are fine here. I'm just going to write y equals -1/5. Horizontal asymptotes, you may recall from previous classes, if the numerator has a smaller degree than the denominator, which it does here, the numerator has a degree of 1 because there's 1x, denominator has a degree of 2 because if you multiply x times x you get x squared. If the numerator has a smaller degree than the denominator, the horizontal asymptote is the x-axis, which is the line y equals 0. So let's put everything together here and we can base it off of the graph that we see here as well. We're going to start with our vertical asymptote at 5, 1, 2, 3, 4, 5, and we'll do our vertical line here, dashed, 1, Horizontal asymptote at y equals 0, that's your x-axis. I'll draw that on top of our existing x-axis. No x-intercepts. We have a y-intercept at -1/5, so I'll do a tick mark here for -1, and our y-intercept is right below it. And we have a hole at -2. More on this in just a moment. So what's our graph going to look like? Well, there is a hole at -2, and if that hole wasn't there, we'd have our graph that would come through the y-axis here at -0.2 or -1/5, and then crawl down here, and then you can see the graph picks up again over here. This part of the graph is fine the way it is. Over here, we have our asymptote kind of coming up through here. We're going to go through our y-axis value here at -1/5, and we're going to continue going this way, except that at -2, we're going to put a hole in the graph. Now, what's it going to say on the table on your calculator? Well, if we go to second graph, at -2, it does say error, which means nothing happens there. If x plus 2 is only in the denominator, that would be a vertical asymptote. Because we see the same factor in both the numerator and denominator, it's called a hole. And if you think, well, can't I just cancel those out? You could, but in our equation, there's no value at -2, so if we canceled these out, you wouldn't have a hole here. For the second equation, let's start with y equals x times x minus 3 over x minus 3 and talk about the parts. It appears that there's a vertical asymptote at 3. However, we have the same factor on the top and bottom, so x equals 3 is actually a hole. There are no unique vertical asymptotes in this graph. In the numerator, this will tell us about x-intercepts. There's going to be an x-intercept here at 0, because if you plug in 0 for this x right here, you would get 0. It appears that 3 would be an x-intercept. However, x minus 3 again is on the top and bottom, so it's not an x-intercept. It's not a vertical asymptote, it's a hole. So the only unique x-intercept here is x equals 0. The numerator has a bigger degree than the denominator. The numerator has a degree of 2, denominator has a degree of 1. Because numerator has a bigger degree than denominator, there are no horizontal asymptotes. And the y-intercept is found by plugging in 0 for x. If you plug in 0 for x here, you're going to get 0 times negative 3 over negative 3. Well, 0 times anything is 0, and 0 divided by anything is 0, so the y-intercept is 0. This doesn't give us a whole lot to go from. There are no vertical or horizontal asymptotes. There is an x-intercept, which is the same location as the y-intercept, which is here at 0, 0. Let's take a look and see what this looks like on our calculator. On your calculator, it appears that we just have a line, and we almost have a line here. We really almost do. The graph goes right through here, but there is going to be a hole at 3. So as our graph goes through our point, our x-intercept, once we hit 3, there's a hole in the graph, and the graph continues on. What this line would be what you would get if you canceled out the x minus 3's. It's actually the line y equals x, but there's a hole at 3. So to reestablish how to find the components of a rational function graph, these are the 5 parts that we've identified in the last problem. What we call points of discontinuity are points where the graph is separated. Now there are 2 types of points of discontinuity, things that we call holes and then other things we call vertical asymptotes. Holes occur in places where we have the same factor in the numerator and denominator. And the hole is located at the 0 for this factor, the value for x that would cause us to get 0 for that factor. Another example of a point of discontinuity is a place where vertical asymptote occurs. This occurs when we plug in a value for x in the denominator and get 0. Other components include x-intercepts, y-intercepts, and horizontal asymptotes. X-intercepts are values for x that cause the numerator to equal 0. To find y-intercepts, we plug in 0 for x and we figure out what y is equal to. And there are 3 options for the horizontal asymptote. Remember that the horizontal asymptote could be the horizontal line y equals 0 if the numerator has a smaller degree than the denominator. There is no horizontal asymptote if the numerator degree is larger than the denominator degree. And the horizontal asymptote is equal to the quotient a divided by b if the numerator is equal to the denominator. Remember that a and b are the lead coefficients of the numerator and denominator. Okay, now let's put all this together and see if we can graph an equation that features holes in vertical and horizontal asymptotes and x and y intercepts. Let's take a look at this first example. I've taken the time to already type this in my calculator, and we're going to graph this function. On the calculator, again, some of you may not have a vertical line here, but I think everybody should have kind of a curve here. We've got some curves going on in the middle, and something else kind of going on in here. Points of discontinuity would include things like vertical asymptotes and holes. So first of all, we can identify holes by factors that we see in both the numerator and denominator. I see an x plus 1 in both the numerator and denominator, so that's going to denote that there is a hole at the value that would cause that to equal 0, and that would be x equals negative 1. There are a couple of vertical asymptotes. They're located at x equals 6 and x equals negative 3. In the numerator, we can identify x-intercepts by values that are not holes that would cause us to get 0 in the numerator. Now we know negative 1 is one such value that's a hole, but positive 4 would be our x-intercept. Our y-intercepts are found by figuring out what we get when we plug in 0 for x. If we plug in 0 for x in the numerator, I'm going to get a negative 4 and a positive 1 that are going to be multiplied together. In the denominator, I'm going to get a positive 1, a negative 6, and a positive 3. When you multiply all this out, you get negative 4 over negative 18. That's equal to 2/9, or 0.2 repeating. So there's your y-intercept. The only thing left to find is the horizontal asymptote. In this example, I see 2 x's up top. That's kind of like x squared. On the bottom, there's 3 x's. That's kind of like x cubed. So the degree on the top is smaller than the degree on the bottom. That means the horizontal asymptote is your x-axis, or y equals 0. So what is this going to look like? I'm going to start with my vertical asymptotes first. I'm going to graph x equals 6, 1, 2, 3, 4, 5, 6. And we'll draw a vertical line. We have a vertical asymptote at negative 3. 1, 2, 3. Draw a vertical line there. X-intercept at x equals 4. Y-intercept at 2/9. So I'll put a tick mark there for 1, and then we have 2/9 is just above the x-axis. Horizontal asymptote of y equals 0. And there'll eventually be a hole at x equals negative 1, which we'll deal with. You can see in the bottom left corner of our graph, we have a branch down here. You can see that our branch in the middle is going to kind of follow this asymptote, go along here, cross the y-axis, cross the x-axis, and make its way down. And you can barely make out, but we also have our other branch that does something like this. And there's our graph. What I'd like you to do is I'd like you to try out this other equation. The points of discontinuity are the holes in the vertical asymptotes. Let's see if you can figure out the points of discontinuity as well as these other key features while you graph this last equation. Pause the video for just a minute and we'll see what you come up with. So first of all, we've typed our equation into y equals menu of our calculator. We've also graphed our equation here. There is a hole in our graph because we have two of the same factors in the numerator and denominator. The factor is x plus 5, so the hole is at x equals negative 5. Vertical asymptote at 1.5, because if you plug 1.5 in for this x in the denominator, you would get 0 for this factor. There's an x-intercept of 0, because if you plug in 0 for this first x in the numerator, you get 0. The y-intercept is equal to 0, because if you plug zeros in for all of these x's, what you would get is 6 times 0, which is 0 times 5 over negative 3 times 5. And because there's this 0 up top, 0 times anything is 0, divided by anything is still 0. So there's your y-intercept. Horizontal asymptote, you'll notice that there are 2 x's in the numerator, 2 in the bottom, so it's kind of like we have 6x squared, and we also have a 2x squared. When you divide those lead coefficients, you get 3. Y equals 3 is your horizontal asymptote. Now let's graph these different parts. The vertical asymptote's at 1.5, so we'll do 2 tick marks, and we'll do a vertical asymptote at 1.5. Horizontal asymptote at 3, so I'm going to go up 3 units and do a horizontal asymptote there. X and y-intercept at 0, put a point there. You can see by our graph that we have a graph that features a curve that follows the asymptote and then curves down like this. Because there is a hole at negative 5, I'm going to graph it from right to left. So you'll see my graph come up like this, cross, get close to the asymptote, hole right there, and then continues on. We also have on the right side a branch that goes like this. So there's your graph, and now you know how to make a graph that features both horizontal and vertical asymptotes, x and y-intercepts, and holes in your graph as well.